what we have done in the beginning of the lecture, the calibration of measurement devices. A few questions. No questions. Okay, then I start with the lecture of this week. What you see here is the characteristic of a differential configuration. That's what we have done according to my notes. We have done this in the last lecture. Important is when you have, like here, when you have sensors which have a non-linear curve, but when the non-linear curve is has a physical reason, so that it is every time exactly the same, then can you use the differential configuration to get an linearization. You see the middle plate is going up and down, and when you increase the capacity on one side, you decrease the capacity on the other side. And you see here this drawing, this is C1. This is the way of the middle plate. And you see here how the curve would go when you have only one sensor. You start with a capacity, and then when you make the distance between the plates bigger, the capacity will decrease, and theoretically in an infinite wide distance you come to zero, theoretically. And the other capacity, you go in the same way, but opposite to the first capacity. This y-axis is also a positive axis. That is important. That means with this capacity, you start here, and when you increase the distance, then you get a lower and lower capacity value. But because both capacities are part of a bridge, in this case, it is then a half bridge, two sensors in a half bridge. Because these sensors build the difference between both sides, you have exactly the same capacity when you are exactly in the middle. So that you have the half of the voltage on one side and the other half of the other side. And when these two resistances are equal, when they have the same value, you have also here the half of the voltage. A half on the left side, a half on the right side, so that the difference is zero. And that would be this point. The way 1 and the way 2 is the same. So you are here in the middle, and you have as a difference 0. But when you go now up and down and calculate the difference, you see that you are in a wide range linear. That is the most important point for the differential configuration. You can make a linearization of the sensors. And additional, you have the double sensitivity, because it is a half bridge. A half bridge has the double sensitivity like a quarter bridge. And you have an impression against disturbances from outside. When you have disturbances from outside, you have it on both sides of the bridge. And when you calculate the difference, then you eliminate these disturbances. So that you can say you have three very important points with the differential configuration. You have the linearization, you have the double sensitivity, and you have an elimination of disturbances from outside when they have an influence to both sides of the bridge. And therefore, many sensors which are linear and where you can give your measurement value in the direction and opposite direction on, then it is very often used as a differential configuration because these three advantages. Yeah, you have it here. I have here a small task to calculate the diagonal voltage from the voltage from the power supply of the circuit and from C1 and C2 under the condition that the two resistances are equal. And I show you the result. It is, you say this is a voltage on one side, this is a voltage on the other side, and the diagonal voltage is in this case, the right side minus the left side. This is a voltage over this resistances, the total voltage to the total resistance as this voltage to R1 to this resistance. And the same you do on the other side. That would be this. And then you can set R1 is equal to, then have you on one side only the half of the power minus the other side. And then you can transform it and can set the capacity resistance is 1 divided by the frequency multiplied with the capacity. Then you get this huge double break that is difficult, but you can short many things. And if you see this formula, here you see the diagonal voltage is the half of the power multiplied with, and that is now important, C1 minus C2 divided by C1 plus C2. And this means it's working against each other. And so you have an linearization. Have you questions? Okay, then let me show you a little bit faster because that is easy to understand. You can read it also in your script. Different other sensors for distance measurement. Also, this is a sensor which is very sensitive when you have very small distances here. You short the way of the magnetic fields and you have a low magnetic resistance in the iron, but a high resistance in these two gaps. And when you make this gap smaller or wider, then you have a change of the inductivity. You see it here. And also here, Yeah, you see here the derivation of the formula. You have the inductivity is equal to the, let me say, the inductivity when you have no air between this, and when you go far away, you have then 1 plus, that is the relatively permeability for the iron, and you have 2s, that's the way you see here, this way, divided by the way in the iron, that would be this, and this would be this. And when you go with your way to an infinite long distance, then you see this would be infinite. But when it is infinite divided by the iron, let me look. No, this the S in the iron will be infinite. So that so that expression would be 0 in the end when you go in an infinite way far from the sensor, and then have you this expression as 0, and here is then written the inductivity is L0, the basic inductivity, divided by 1, so L is L0. And when you have when you go to the right side, and this gap will be bigger, you have an higher resistance, that means a lower inductivity, so that you are, when you are infinite away, then have you only the inductivity from this, and this is then L0. Few questions. These sensors are very sensitive when you have small differences here. When you have small differences, but in practice is the problem when you have little metal pieces which are going between this, or which are going into this gap between these both sides, then get you really hard distortions of the function of the sensors. That means you must be sure that there is no metal powder or kind of metal pieces which can disturb the sensor. That is a disadvantage. But on the other hand, when it is completely free of metal powder, or when the air is completely, the air or the oil, you can set it also in oil, when it is completely free, then it's working extremely sensitive in the range of micrometer as a gap between the sensors. Yes. Also, this sensor you can run in a differential principle. You see here, this is the middle, the anchor, and you have one side, the sensor, you have a second sensor on the other side, and both have together this anchor, because also from this sensor you have the same as with the capacitive sensors, when you go away, it comes against zero. The inductivity comes against zero when you are with the infinite distance from the own anchor. Of course, here you can not come to an infinite, but you have a nonlinear function, and so you have again exactly this differential principle also for this sensor. Here you see a single sensor and again a differential sensor. Yes. Have you questions to the inductivity as distance measurement sensors? No? Then we have a lot of principles, but you can make two groups. We have incremental measurements and we have coded measurements for the length. Both, here we have the incremental and here we have the coded. Both are exist in many solutions. You can make it with light, you can make it with contacts, with small switches. But what is important is that we have two fundamental principles. Incremental means you count. You have here the white and black stripes, and when you move this bar, then have you an impulse, and you can count these impulses. The incremental principle is normally easy to realize, but the incremental principle has a huge disadvantage, and the disadvantage is that you don't know where you are, because you count every time, plus maybe in this direction, plus in this direction. But when you are in the middle of your scale and you switch the machine off and switch the machine on, you are here at zero. And when you are at this place and you switch the machine off and switch the machine on, you are here on zero. That means when you measure with the incremental principle, you have to define at first your 0 point. So that you say, when I switch the machine on, I go to this side, set the counter on 0, you set the counter reset, and then you can add and can subtract so that you have every time the right point. An additional disadvantage is when you have a mistake in your counting. Maybe there is a hair in or piece of paper or what else. When you have a mistake, then you will have this mistake also when you count up and down until the next reset, until the next time when you set your measurement system on 0. That is important. What can we do that we have not these disadvantages? When we won't have not these disadvantages, we can use the so-called coded measurement systems. The coded measurement system have, for example, a dual code, and you have here the possibility to take the value via light or via switches when this is metal and this is plastic. then can you also go with switches on. And important is when you are in the middle here and you switch a machine off and switch a machine on, you have exactly this position, because every position is coded. The coded systems have, let me say, are more expensive because they are not so simple like the incremental principle. But the coded system has the advantage that they have for each position a clear value. Now have we with the dual code a problem, because it can happen that more than one points, more than one bits change to the same time. You see here from high to low, from low to high, from low to high. And such a point is a question, who is the first? I will show you that. Let me look. Now should you see my drawing? And let me say we have a 1. That's a 1. And that's a 2. And that is a 3. That means 1, 2, 3, because that is 2 powered by 0, 2 powered by 1. And when you add this, you get 1, 2, 3. And now is the question, what is doing the system when you switch, for example, from 1 to 2? You can have that at first the H will go to 0. Then have you a short time 0, 0. It can also be that the 0 will be at first an H. Then have you a short time HH means 3. Also in this case, you can have the same, that you have here between values which are not 2 and not 3, because 1 is the first, 1 is the second who is switching. And that we called races. Races like a horse race also. The question is, who is the faster as the other? And when you have races in the most significant bit, you jump between the switches in a wide range, in the half of the range. When you have a race in the most significant bit, it's representing the half of the total range, so that you get big jumps between the clear values. And that have we to avoid. That have we to avoid. And therefore, we can work with the so-called gray code. The gray code, it's a code where the only one thing is that we have every time only one change, so that you can have never erase. The disadvantage is that this is more a picture. With a dual code, you can calculate the number, but with a gray code, you cannot calculate the number. Therefore, is here written grade 0, grade 1, grade 2, grade 3. That means that is like a picture. That is not to calculate like a dual code. And you need, therefore, when you use the gray code to avoid races, you need an electronic where you calculate from this picture, this calculating dual code, where you can calculate your number. That means you need an additional electronic to come from the gray code to a calculated code like a dual code. But then have you no races. It is more electronic, more difficult sensors, because I have only 4-bit at this moment. But when you would like to have an high resolution distance measurement and you have 12-bit or so, then you need 12 lines to build the code. That means the coded measurement systems normally are not so easy to realize like incremental measurement systems. But on the other hand, you have many systems which are coded and work analog. Our, let me show it here. Our diving sensor is a coded sensor, because when he has one position, you can say you switch the machine off and again on, and you have exactly the same position. That means this is also an analog coded sensor. What you should know is the difference between incremental principles and coded principles. And you see, no, I have not. You can realize both principles in a different way, but you must every time know, is there a coded system or is there an incremental system, with all disadvantages and advantages of the both principles. Have you questions? No? Then we go to the triangulation principle. That's a distance measurement system where we try, or where we measure with a laser, but it should be independent of the color of your measurement object. So you look on this point, you get here the scattering light, and you look here, the scattering light, that is a CCD line, and you have here the small pixel on, like in a camera, and you see how this is moving on this CCD line, and you can calculate or can calibrate this with a distance from your measurement object to the point of the CCD line what you have. And when you have when you have an, let me say, a white plate, the point is brighter. as from a dark plate, but you have it on a special position. And what you use for the distance calculating is the position and not the amplitude of the scattered light. These systems have not so a big precision. Normally you are in the range of a part of millimeter, a part of a millimeter, 0.5 millimeter, for example. But when you are, for example, in a factory on a construction belt where devices are constructed, and this device has to stop on a special position for the worker that they can handle that. For such a task is the triangulation principle developed and is used. A few questions. Yes, I think I can make it a little bit faster. The CCD line plays a big role in many measurement systems. For example, when you measure a wire, the diameter of a wire, you get a shadow on the CCD line. And with this shadow, you can calculate the diameter and can check it. Very important is the so-called interferometer, because the interferometer is a distance measurement system, but it is measuring also, it is used also, for example, in balances. When you would like to determine the mass, you need only then a body which where you put your mass on, and you get a very, very small change of the position. How is the principle? You have a laser, and you have here a mirror where 50% is going through the mirror and 50% is reflected. These mirrors are standard mirrors. You can buy it in every size and so on. And you can exactly say how much should going through, how much should reflected. But in this case, we need the 50-50 mirror. From the laser part, 50% is going through and 50% is going in this direction. And then you have here a reflector. This reflector is fixed. The other reflector is movable. This reflector you can move, and this reflector you can fix, so that you go with the half of the beam in this reflector. It will reflect it 2 times and go back again to this mirror. And so this beam will again split it. 50% is going in this way, 50% is going this way. When you now have here the same, but this reflector can move, then get you a phase shift between this part of the beam and this part of the beam. And that means when you look from this direction into the beam, then you see when you move in one direction, these rings are going to inside and are in the middle point in the beginning. And when you move in the other direction, you create new rings which are going out to outside. so that this is moving or changing. And when you see the rings are bright and dark, and when you measure between bright and dark, you have the half of the wavelengths. That means you measure a difference in the way of the half of the wavelengths when you change from bright to dark. And here you can set a receiver that can be a phototransistor or a glass fiber in this case. That can be different, but you must only count. And you have the formula that the way what you have moved your sensor is the number what you have count multiplied with the half of the wavelengths. Half of the wavelengths between bright and dark, that is the half of the wavelengths. But that means that you can measure, for example, when you measure with red light is so in the range of 680 nanometer. That means you can measure with, when you count only bright and dark rings, that you can measure 340 nanometer. That's a very high resolution, a very, very high resolution. That is the one advantage. There is also a disadvantage. This is a typical incremental principle because you count up and down. The rings are going to outside or to inside. You count up and down, and you have to say where are you at the 0 point. That means when you have a balance, for example, and I change to the drawing field. I think I must need a little bit bigger. When you have, for example, a balance, here this is fixed, and the movable is, for example, here. No, that's wrong. I must. No. No, I must have a look how it is. I look in the other. Yes, I need the peak. The first was right. The first was right. You have it so. And this is your balance, where you go then with your laser beam here in this direction. And when you put something here on top, that's a mass, what else? And then have you an extremely small movement in this direction. But when you have red light, 680 nanometer, and you change 340 nanometer, then have you from the rings, from a bright ring to a dark ring. That means the principal would count 1. And when you move a little bit more, it would count responding more. You have to set it 0 because it is an incremental system. That means you take this mass away. You take this mass away and set now the counter to 0. And then can you calibrate the system with different masses. You can calibrate the system in kilogram or what else. These balances, we will also see at the balances, this principle, are very fast, because a balance can you only make faster when you have small ways. When the way is too big, you can also get an oscillating system. But in this case, you have a really small way, so that the balance is also very fast. Yeah, that is the interferometer. That is the interferometer. And an additional advantage from the interferometer is that you have a high resolution, but also a wide range. Normally, you have when you have a wide range, you have not so a high resolution. Let me say, when you have a balance in the range of kilogram, a normal balance with a spring, for example, when this balance is working in the range of many kilogram, then have you not the resolution in the microgram range. And when you have a balance in the microgram range, then can you measure maximal some gram, but not in the range of kilogram. But in this case, you have a high resolution, but because you count only, you are nearly unlimited in the range. It's only depending from the counter. And theoretically, a counter you can set up with an infinite range. That is a very important point for the interferometer, that you have both a very wide range and a very high resolution. That is the advantage. Have you questions? No questions? Okay, then let me show you some length measurements, for example, with ultrasonic. You know this distance measurements, for example, from the cars, when you have a parking system inside, then it is often used ultrasonic. And how to produce these ultrasonic waves and how to measure. The core is a piezoelectric effect. You have a piezoelectric material that can be silicon dioxide, but there are also other materials where it works. How works that? Important is that all molecules have the same direction. And for this, for example, you can use material where you melt this material and you let it in a magnetic field. You give it in a magnetic field so that they have all the same direction, and then you cool it down. Or when you have silicon dioxide, you can make it with the process of the semiconductor production, where also all molecules have the same direction. Now we give a pressure on this sensor. You charge the sensor, and he will extremely small, a little bit pressed together. But because that is a solid material, you can nearly no measure this. This is in the range of nanometer. You can measure this with the interferometer, but that is the only one chance to measure this small change of the thickness of the material. And now we look what will happen here. What will happen here? And I go again to my drawing. You have, for example, the upper and the underside, and you have here the silicon with a positive charge and O2. Well, let me make it so. O2 with a negative charge. And every charge has a field around. Every charge has a field around, which is positive, but is decreasing in the power when you are more far away. You decrease the power. When you have it here, I make it a little bit. You have here this charge. This is a positive charge. And here you have the negative charge. When you now press it together, you come closer to this positive charge. That means the electrons will attract it to this to the surface. The surface is covered with a metal, and you get here the positive charge because the lack of negative electrons. On the other side, it's in the other way. You have here minus, and you have here plus silicon dioxide. And when you come to closer to the negative charge, then the electrons will go away. The electrons will go away, and you get a negative charge of this plate. And when you now connect a resistance, when you now connect the resistance and you set the pressure, the charge on, then you will have that the electrons are going to this side so long as the pressure is there, but until both sides are again neutral. That means when you set the pressure on, you will have, that is the pressure, you will have an increase of the electrons, but NUN is the charge. The charge has an equalization. Both sides have then the same charge. That means these sensors are only used for dynamic processes. It's not possible to use them for static measurements. When you go, I will make this so, and when you go now in this direction, you are here with your pressure. You are here, and you will have this in the other direction. You will have the flow of the electrons in the other direction until it is again 0, so that you have both sides the same electrons or the same charge. And this can you do, let me show it here. This can you do that you use it as a sensor when the pressure comes from outside. That can be the ultrasonic waves, but you can also produce the electronic waves when you set a voltage on the same sensor, on the same material. That means an piezoelectric sensor can work as a producer for ultrasonic and can also work as a sensor for ultrasonic. And this is used in many applications, that you send a small beep, let me call it beep, a small beep you send, and from the reflection you get it back, and you can measure the response of the beep, and you can measure the time, how long is the ultrasonic on the way. And you get reflections from every change of the material, when you go from air to solid material, when you have a borderline from air to solid material, you have the possibility to measure solid material in water, air to water. All these borderlines between different materials, liquid or gas and so on, is a reason for the reflection of ultrasonic. And what we use in many cars is that you measure the time from the beep to the response. And the only one's problem is when you have a strong absorption material, when you have, for example, snow, then you can send the beep to the snow, but there is coming nearly nothing back, because snow is an absorption of ultrasonic. Also foam is also an absorption of ultrasonic. And so it works only when you have a really borderline between, mostly when you use cars, or the example of cars, mostly between air and solid material. I have a few questions. Yeah, this is a sensor. You see here the surface material. Here have the piezoelectric plate. And these sensors are also used for testing of materials. When you would like to test the quality of materials, you can look, is there a small break or a small gap inside? The interesting thing is that you must not destroy your product, and you can measure 100%. For example, when you have wheels for engines or for bicycles also, and you would like to measure, is there a gap in, is there a break in or not, you can set the sender on, you send your signal, and you know when it must come back. But when you have earlier an response, then you know there must additional to this both sides an additional gap in the material. There are different methods to send. You can use the echo method. That is what I have explained. You send a beep and you listen when is coming the response. But you can also work in resonance. That means you send and receive to the same time. And when you get a phase shift between the sending signal and the response signal, you can look how big the phase shift is, and so can you also use the piezoelectric sensors to measure the distance. A few questions. Yes, determination of angles, that is nearly all the same as the length measurement. You see here the incremental principle, you see here the coded principle. It's the same as with the length measurement. You have here 3 analog sensors, resistance measurement for the angle and capacity. And this is also often used because it is extremely robust. But the disadvantage is that mercury is very toxic, and therefore it is completely covered as a sensor. The working principle is that you have a resistance wire inside, a resistance wire, and you measure, here's the resistance, and here you have mercury. And mercury is a shortcut for this part of the resistance. So when you have it in this angle, then have you here the middle of the resistance. You have here one part of the resistance, here the other part of the resistance, and you are now exactly in the middle. When you turn this sensor, you have the mercury on this side completely. Then have you here 0. That means this point is connected to this point, and you have the full resistance on the other side. Here you have the full resistance on the other side. These sensors are extremely robust and used, for example, in ships, when a ship is on the waves, to look how the position is and so on. Yeah, there have you the sensors. You can give a relatively high current through the sensor. That is an advantage. And you can measure directly without any amplification and so on That's the advantages. So strong connected to the distance measurement is also the position measurement. When you would like to measure the position of a body, and for example, when you have a material in a drilling machine and you would like to make an automated position determination so that you can drill it on the right point. Very easy, but not very precise are the one-way light barrier and the reflected light barrier, because it is then every time depending when the body is in the beam, it's depending from the sensitivity when the device is switching. That means the beam has an diameter, maybe in the range of millimeter. And then it's a question when you come into the beam, when is the device switching? When says the device, this is the position. You can not have a higher precision as a diameter of the beam. That is a disadvantage. It is a very easy construction, and when you need not more precision as a diameter of the beam, then it is easy to realize. The question is, what can we do that we get a higher resolution as a diameter of the beam? And for this, we have gap sensors. With one gap or with two gaps, here we have two gaps. This is a photodiode, and we have a small gap in Y and in X direction. It's burned with a laser, so that you have 4 single photodiodes on one chip. 4 single photodiodes. And when you go now with a beam on this, you can have the beam on all photodiodes and can look what is the voltage, what is the current from each photodiode. And when you are exactly in the middle, you have equal currents or equal voltages from each photodiode. And that means you can realize precision which is smaller than the diameter of the beam. So you need not an expensive optic to form small beams. The beam can be a little bit bigger. It's no problem, because you compare the irradiated area on each photodiode. That works also with one. When you need only in one direction, then you have a single gap sensor. But when you would like to determine the position in 2D, in X and Y direction, then you need a gap sensor with 2 gaps so that you can realize this. Yeah, have you questions? Okay, now, sorry. Now we have an example for the calculation of the power. but I think I skip this example because the most of you are not from the electrical studies. So I think we skip this example. That was to calculate the maximum power of a sensor with the inner resistance and resistance. It's like a shortcut that you get an shorter switching time. But I think it is not so easy to understand when you have not the fundamentals of electrical engineering. Therefore, I think we skip that. Yes, other circuits measure the distance or what else with the magnetic field. And interesting are the so-called Hall circuits. The Hall effect is a semiconductor, normally every time a semiconductor, but it works also with conductors, where you give a current through. Here you have a current. The electrons are going from the right side, in this case, to the left side. And when you send or set it in a magnetic field, the electrons get a drift, in this case, to the upper side, so that you get that the electrons make a bow caused by the magnetic fields. So you get here more electrons, here less electrons, and you can measure minus and plus here the voltage. When you have no magnetic field, all the electrons make no bow. They go from the right to the left side, and you have zero. The typical current is 100 milliampere until 500 milliamps. You see the current is relatively high, but you can measure 50 millivolt to 400 millivolt. And on the other side, that are good values for the processing of the signal. The characteristic is so that you measure the voltage depending from the magnetic field. That is linear. But when you would like to measure a distance, then is B nonlinear from the distance, so that you get, again, a nonlinear function. When you would like to measure not directly the B, when you would like to measure the distance, then it is nonlinear. But you can also detect in which direction the B is. You see, when the B is in the other direction, you have the electrons to this side, and you know here in which direction is the magnetic field. When you would like to measure a position with a Hall element, then it is important that you have a strong decrease of the increase or decrease of the magnetic field. And therefore, often we use this form, this shape, that you have a north and a south directly in opposite, so that you have here a very strong increase of the magnetic field when you go with your Hall element into this magnetic field, so that you have a relatively good precision to switch. The advantage is you have no light influence. All the switches where you work with light have the problem that light is one of the most important disturbances what we have in processes, and here you have no problem with light. You can set it in oil, you can make it in air. The Hall elements are normally not sold as an poor element. Normally it is sold directly with a current source, with the amplifier, and then have you an output, mostly a switching output. It exists also sensors with the analog output, but that's very rare. Normally, the circuits have a switching output, and then can you measure very easy the position of the element or the position of the permanent magnet. A few questions. No, then, yeah. In the principle, this field plates is the same. You have one side and the other side, you give the current through, but I switch back. You measure not the voltage, which is caused by the magnet field. You measure directly how the current is decreasing when the electrons make a bow caused by the magnetic field, so that you have only two connections. And you see here you have embedded metal needles, so that the electrons take the shortest way from needle to needle, and you come on a shortest way to the output. But when you have a magnetic field, then you get an elongation of the way of the electrons, and by the needles you force this longer way, so that you have then an decrease of the current. The disadvantage is this is nonlinear, and you cannot say in which direction it's working. You have an basic resistance, that would be the resistance over the element without the magnetic field. And to both sides, when B is going to this side or to this side, on both sides you have an increase of the resistance. On the other side, it would go in the opposite direction. You have the same effect, but the resistance can only increase. And you see not the direction of the magnetic field. But these elements are extremely cheap, and when you use it, for example, that you would like to know what is the biggest magnetic field on a trafo also, then can you use these field plates. And then we have on a, let me say, nearly same principle, an extremely sensitive sensor, where these field plates are in a bridge. That is the first point. They are in a bridge. And we have a little bit a different effect, the so-called anisotropic magnetoresistive effect. That means these stripes are extremely thin. We have a coating thickness from less than 50 nanometer and a width from round about 10 micrometer. This width 10 is 10 micrometer. And when you have a current through this, then can you set a magnetic field on, and you see the diagonal voltage, that is the output of this. When you see, so it is a small Wheatstone bridge, a full bridge with 4 resistance, and you see you have an increase of the diagonal voltage until one point, and that is a point when you are with 45 degrees, when the current is going with 45 degrees to this plates, and you see when you are here, then you are parallel. That means the resistance is going high, the high resistance, when you go parallel with the electrons. And here you have the shortest way when you go in this direction. But when you are over a maximum, then it will be here longer. The way will be again longer. You get a higher resistance, and here you come again closer because you get a lower resistance. And therefore you have this turning point where the diagonal voltage is going again down. The same have you in the other direction. You can work in this area from here to here. It's nearly linear. And the advantage of these sensors is that they have an extremely high sensitivity. You can measure the magnetic field of the Earth, and for this are the sensors also developed. And we have done tests with the sensors as they was new in the market a couple of years ago. They are not so old. We have tested the sensors, and we was able to measure the magnetic impulses from a clock, where you have a small switch motor in, and we was able to measure with this sensor these magnet impulses from a clock. The one other advantage is that you can calibrate with a constant magnetic field. That means with 0 frequency, 0 hertz, until the range of megahertz. That means these sensors works for static magnetic fields and for dynamic magnetic fields until the range, in the megahertz range. Disadvantage is low linear only at low field intensity. You see only in this range. They are also sensitive against temperature, but the sensitivity against the magnetic field, that it is so high, is for some applications a huge advantage, but for many other applications where it is too sensitive, it's a disadvantage. It's depending from that what you would like to do. And normally the magnetic field of the Earth has already an influence. But when you would like to measure this, then is it an advantage? Have you questions? Okay, then we come to strain gauges. Strain gauges are very important in mechanical engineering, especially. And with strain gauges, you can measure the stress of a material, but the most of the applications measuring some other things like the mass, for example. You have strain gauges also in many balances where you get a stress from which leads to a deformation of a measurement body, and you measure then via the strain, via the stress of the body, you measure the, let me say, the mass which is on the balance. You have two different kinds of strain gauges. One are metal strain gauges. And you see here, you have a wire. You extend this wire. And when you extend this wire, it will be longer and the diameter will decrease. This are, let me say, the original form of strain gauges, but today we use normally layer strain gauges. The effect is exactly the same, but we have not a round wire. We have a layer flat on a board from a kind of plastic material, and you have here this long wire on, but flat on the underlayer. And when you measure in this direction, you have here more changes than here. And when you measure in this direction, you have here more changes as here, so that you can also measure depending from the direction. But the principle is the same. Both are metal strain gauges, and you can see that you increase the resistance because the wire will be longer and smaller. This effect is called form effect because the form of the change of the shape is the reason for the change of the resistance. And then we have a semiconductor strain gauges. Semiconductor strain gauges, that is a semiconductor material. And of course, when you elongate this material, you have also this form effect. But much more sensitive is a change of the specific resistance, because the semiconductor strain gauges are very sensitive when you elongate or compress them, that they change the specific resistance. The problem is that we need to make both kinds of strain gauges independent from the temperature. That is the biggest problem. And we can do this with the metal strain gauges in a bridge. We can do that in a bridge. That is very easy. But we will see the metal strain gauges are not so sensitive like the semiconductor strain gauges. But how we make it that we have no influence from the temperature with the bridge, that I will explain you in the next lecture, because I need a little bit more time for this. The semiconductor strain gauges have the problem that every strain gauge is a little bit different from the other. So that the influence of the temperature is not the same on every strain gauge. And therefore, it don't work when we use a bridge, because the temperature coefficient must be exactly the same to eliminate the influence with the bridge. And therefore, the most strain gauges, what we use today, are still metal strain gauges, because with metal strain gauges, we can produce strain gauges which have all the same temperature coefficient. And that is not possible with the semiconductor strain gauges. And therefore, for semiconductor strain gauges, we have to measure additional the temperature. We have to calibrate each strain gauge different from the others. And therefore, you will find semiconductor strain gauges only in mass products like blood pressure measurement devices, where are produced a huge amount, so that it is effective to set up a whole calibration circuit for each strain gauge. And this is only useful when you have a really mass production. But for example, balances to measure the mass, when you buy a balance to look how heavy you are, then in 99% of the applications you have metal strain gauges, because balances are not sold so often like blood pressure measurement devices. So I think, yes, the time for today is over. Next time I explain how it works, but the next week we have no lecture, because I am in Malaysia next week. But then is until the end of the semester, we have the lecture and additional the laboratory work in presence. And I upload you in the next days the plan, who is one doing the experiment number 1. Have you questions?
Yes, Professor. I have a question, but not regarding the laboratory.
Yes.
When will be the exam?
There is that is planned by the administration.
Mm-hmm.
I don't know. I think they have not announced that the time, but it is in June.
In June, okay.
Yes. It is in June, and I have written also to the administration that they set our examinations in the first 1 or 2 weeks, that you must not wait so long.
Okay. Perfect.
When they have announced the exactly time, I inform you. Important is that you register for the examination.
Yes, okay.
Your body know how it works. Please ask your buddies that you are registered for all examinations in the quality engineering course.
Okay, perfect.
The questions. So when you have no questions, then I finish the lecture and I wish you a nice sunny day. Bye-bye.
Bye. Thank you.
Bye. Thanks.
Thanks. Bye.